time, and the model W. And the W in this case is going to be, has to match the units here, so this is units in distance, and this has to be units of time over distance, which is called slowness. What are we missing here to make this more general? An old linear model that explains the data here. Abdullah.
Come again, please.
Here we have a simple model, linear model.
Yeah.
Okay, that explains, hopefully the W will explain the data. That this is predicted times, this is observed times. So what are we missing here to make this more general?
The bias.
The bias, okay. So we already did this problem. We did the least squares, and we talked about that. At least for a linear relationship, we have the least squares and the gradient method that Abdullah came up with. Showed that. Now I wanted Abdullah to do before the class a little code. The problem is we had other people here, so we don't have time. I don't want to waste time. But tomorrow, can you do it tomorrow?
Okay, in the lab?
Yeah.
Sounds good.
So sorry. Okay, so we have the residual there. Then we have this adjoint, which we also note the adjoint applied to the residual is the gradient. Well, if we're going to do a classification problem, then everything looks the same, except this right-hand side. What's the difference, Abdullah?
It's this is only 1 and 0.
1 and 0.
Yeah.
So on the right-hand side, outcome is restricted to a very small range of numbers, integers in this case, 0 and 1, then that's typically a classification problem. So we're going to solve this problem by the neural network procedure. Okay. Now instead of having trial time offsets, x1, x2, x3, where we timed our visit by the motorcycle to the timer, we're going to call these guys x0, x1, but not stop at x3, but go all the way to xn. So this will be a row of what? Lookman.
Pixels?
Pixel intensity values, and turn this into a grayscale value, and we know how to flatten that picture into a bunch of numbers between, say, 0 to 255 or 1 to 256. Okay. And this side is going to be a classification. And we're going to say if it's a motorcycle that's red, it has a value 1. If it's not red, it has a value 0. So it's a binary classification. So these are different photos of motorcycles you throw in there. Notice they're rows, so the X's are rows. And in this row, did we have a red motorcycle, Abdullah? Did the intensity values in our photograph?
Yeah.
How about this row?
No.
I've had 17 motorcycles. So this is a different color, so that's the different color one. I mean, I don't have 17 now, but I have. In my lifetime, I've had 17. Okay, so anyway. So they're sparse, and they only cover a small range of numbers. And how we're going to make this work is because if you try to solve this problem this way, it's not going to work for you. Because the output is, you can take anything you want for the predicted output. But here you want to restrict yourself to a very small range of numbers, between 0 and 1. And so you're going to have to add something else to this guy, and that's the traffic cop that's going to decide if it's going to be a 1 or 0 or anything in between. So I used to call this a sigma, but to be more general, we're going to get used to this idea. Also call this an activation function. We're going to often call this an A instead of a sigma. Because sigma is not just going to be a sigmoid function, it could be a lot of other activation functions. And so we symbolically are going to try to fix this problem this way. So this is our classification problem, nonlinear classification. This is our linear regression problem. Notice there's no sigma here, just a summation. Here's a sigma and a squashing function. And you're going to find out that the only difference between the update from Abdullah's old code to the new code is one piece of information right here. This is the squashing function times 1 minus the squashing function. That's the only difference. can find this out. So a threshold function. Okay, sigmoid function. Now, I'm giving you kind of an intuitive introduction to sigmoid functions and use of biology and threshold intuition. But it turns out there's some, the statisticians have looked at this, and there's a probabilistic interpretation of this sigmoid function. But I don't want to do it now. Let's wait until we get a good feeling for neural networks, and later on we'll have a lecture on probability and how that's related to probability functions. Okay, let's just use our intuition. And certainly for the first 20 or 30 years of this field, they didn't have any probability associated with it. So we're just going to stay with that. So as we know, this sigmoid function looks like this. As z gets really big, this guy turns into 1, as it should, as z gets really big. And as z gets really negative, really small, this guy turns into something huge. So 1 over something huge is 0. So anything in between is there. And in between there, if you put z is equal to 0 here, what's this turn into at z equal to 0? Abdullah.
Yeah, it's equal to 0 or half.
If what does this function turn into at z is equal to 0?
0, 1.
Is there a clock here?
It's a half, that's all.
So what's this when z is equal to 0, Abdullah?
1 over 1 plus 1, so it's
Just tell me what it is.
it's half.
Half. Okay, so at the midpoint here, it's half. Okay, there we go. And so if you take a derivative of this guy, you can see that it's 0 derivative here, 0 derivative here, and then in between you start increasing positive slope, and then you still have positive slope here, right? You still start to go to 0, and that's what we see. So this guy, depending on if you have a little alpha here, that might tweak the magnification of this argument here. This guy can start to turn into almost like a boxcar. So it resembles a boxcar kind of thing. Okay, Abdullah, is this obvious?
What do you mean obvious?
That is, you take the derivative of this guy with respect to z, it turns into the same thing again times 1 minus a.
Okay,
That's pretty obvious, right?
yeah, if you do it, it's 1 over 1 plus. No, not really.
What?
And
Well,
then-
look at this guy, 1 minus a. What's he plot out as? Like that, right? You subtract 1 from this guy, and you get something like that, right? So you multiply something like this times something like this. The fringes go to 0 on the left and right, and what stays alive is something here, so that's kind of makes sense,
Okay.
right?
Yes, what that is.
Right? So algebraically, I didn't want to do this to take time, but I'll do it real quickly. Just take the derivative of this guy, and that brings this guy down. So it's 1 minus e to the minus e squared. I just looked that up, right?
Yeah.
And then you have to hit on that guy, and that brings out, well, it gives you the same thing, e to the minus e, okay? If you do this quickly, you can check me if you don't believe it. Well, this guy is a of z, and you have this guy left. And you can show that this guy is the same as 1 minus 1 plus minus c to the 1 over that. And you can show that to be true. Well, if that's true, then that's 1 minus a of z times a of z. So okay, z, to remind you, what is z? Well, the z is the is the output of doing the matrix vector multiplication. So in this context, it's a dot product between the w vector and the x input. And I can't somehow, if anybody can tell me how to do this, I'll try to put a w superscript t here. I can't do it in PowerPoint. You can't use your control or something else. I don't know how to do it. So I'm using a prime here. But if anyone knows how to do it, tell me after class.
Okay.
Please. I even tried to drag and drop a copy of that. No. Okay, so this is the observed class, and this is our predicted class. And that's what we have to explain. Is this a linear relationship between t and the right-hand side? Abdullah?
Is T linear or
Is it a linear relationship between t
uh,
and x, input, output, and input? What are some properties of a linear operator?
X is inside the function, so you cannot like take it out.
So what are at least two properties of a linear operator? Quick.
It's, when you multiply
Scaling,
it by constant.
scaling.
Yeah,
Additive.
What's the other one?
I don't know how it's called. It's
Additivity.
Yeah.
Superposition. Let's do the simple one of scaling. So you scale x by 0. So you should get a 0 output. Well, you put a 0 here,
Okay.
e to the minus 0 is 1, so your output's 1/2. Obviously doesn't satisfy the problem.
Yeah, that's true.
Just a reminder. Okay, single node neural network. Now let's go, here's our photos of the motorcycles. MCs mean motorcycles. Where's, oh, she's, excellent. Okay, so here's the red ones and there's the non-red ones. So let's now define the problem very compactly. Given the observed times, try to explain them. This should be an approximation because I'm not going to be able to have this true for all of our data. And the goal is to find the W's that somehow minimize the squared error, some of the squared errors. Okay? That's one way to do it. We're going to find out another way to do that that's even better. And the reason the other way is going to do it, we're going to redefine the misfit function. And we do this in FW all the time. If the old misfit function, this is the W's, and this is the misfit. The old misfit looks like this. But we're going to show you later on, we're going to call it cross entropy. It's going to give us a misfit that looks like that. And why should this be better, Abdullah?
It's the curvature is ours.
It's steeper near the
Yeah.
near the global minimum here. And why is that good?
It makes us converge faster.
Yeah, make a lot of progress. Instead of wandering around some darn valley here, 2D it might be more illustrative. The L2 misfit looks like this, possibly say, whereas this one is more like a beach ball. But I haven't shown you that cross entropy yet, but I will in a second. And not in a second. So, it's important to note we're summing over different flows. So these are, the superscript correspond to the example. And each example input also has an example output. Now in general, this guy could be a vector, but thankfully this is a scalar. Okay, so this is the sum of the squared residuals. That guy is a scalar. For the ith example, and then we have a lot of those examples for some of them. So the first step is that Abdullah says, I'll just take the gradient of that guy, and that brings down to 2, cancels out to half, and you have r sub I times. And what's the residual? Derivative of the residual with respect to wk, kth component. Notice w is a vector now. There's lots of w's. So we have to find a gradient component along each of the coordinates, w1, w2, etc. And this guy's this is fixed, observed. So this guy doesn't survive the derivative, and this is the only guy that survives it. Now, what is this guy? So, what's this recall business, Abdul? Do you recall that?
Recall?
Recall, you know what recall means?
I mean,
Do you remember dude?
Remember, yeah.
Yeah. Do you remember comma dude? Do you remember that?
Yeah, that's the
Okay, we just saw it, so that's
the
okay.
sigmoid derivative.
Yeah, okay. Well, notice here we have a DADW, and the first thing we encounter here is a we can call this guy Z. Okay? Get used to this notation because eventually we're going to get a standard notation for all the elements in our neural networks. And the output of the matrix vector of multiplication, usually they use the symbol Z. Turns out Z is going to be a